Hi everyone. Let's talk about nuclear energy. One way to approach this subject is through a curve that looks like this, called the binding energy curve. And what this represents is along the horizontal axis is we've got the number of nucleons, that is either protons or neutrons, how many particles are in the nucleus. On the vertical axis, we have something called the binding energy. And what the binding energy represents is the net energy that is required to lock the nuclei together. So if you imagine, I start, say, with helium. So I want to combine the two protons and the two neutrons together. And they're far apart from one another, all right? So we call that, let's call that zero energy. There's no interaction. I bring them together. And that's going to require some work because I need to overcome the electrostatic repulsion of the protons. And so I pour some work in, I push. Then they come together, and all of a sudden the strong nuclear force attracts them, and they snap together. Okay? Now that snapping together is going to release some energy. So if I calculate how much energy it takes to push them together, subtract out the amount of energy that's released once they snap together, that difference, the net energy, is what we call the binding energy, and that's what's represented on this chart. And actually, because they lock together, the net release of energy is always a little bit larger than the amount of energy required to get them together. And so that's what's plotted here. And you can see, initially, we start with lower binding energies, and then this climbs up because those larger nuclei, we've got more partners. They actually produce more energy as they lock together, but there's kind of this diminishing returns effect. And so you hit this plateau at the top. The one with the strongest binding energy is actually iron. Iron 56 is the nuclei with the very highest level of binding energy. And then actually things start to fall a little bit as you get into larger and larger realms, just because the nucleus is so bulky that this binding energy just falls as a consequence. So what that means is that if we can induce a reaction of the participants from this energy, and if I can transmute those particles somehow, usually it's just done by slamming them together, and somehow have those particles, those nuclei, either shift, interact, fall apart, it's going to be some random process, but the resulting effect is that if I start with substances on the right side and end up with substances closer to this peak, I actually am going to move up this binding energy. That difference is then released as the kinetic energy of the reactants. Okay? And that kinetic energy then I can use in some form of heat. Maybe I use it in a steam engine or something like that. And that's actually how nuclear reactors work. When I move from right to left, this is called fission. Basically, I start with a large nucleus, and initially uranium-235 was what was used when this was first discovered. And basically, U-235, if you hit it with a neutron at just the right energy level, it will fall apart. The shrapnel that comes out of that reaction is going to be somewhere to the left. That shrapnel is going to have some sort of incremental kinetic energy, which I then capture through some sort of heat engine. It's also possible to go from the left-hand side of the chart to the right. That's called fusion, because basically in that case, you're taking small nuclei, slamming them together, having them lock into a larger atom, and that also produces a net amount of energy. And in either case, you have the production of energy. And that's really where nuclear energy comes from. Now, one interesting side note is that because E equals mc squared, this energy differential actually shows up in the mass of the particles. So if I compare, say we're talking about U-235 again. U-235 splits apart into two atoms, thorium, radium, whatever it is. It splits it apart. You compare the mass on one side of the equation, the U-235, compare the mass on the other side of the equation, they do not balance. There's a mass defect, it's called. That mass defect actually is a consequence of E equals mc squared. The net energy that's released is actually carrying away literally mass from the particles. And so what that means is that just by looking at the periodic chart and comparing the mass of the two types of particles, we can calculate the net energy that's released in these nuclear interactions. And that's what we do in the Homer problems, basically. We imagine a particular reaction occurring, look at the mass differential, use E equals mc squared to calculate the energy, and that gives us a feel for how strong either the fission reaction is or the fusion reaction.